Okay, it's my pleasure to introduce Professor Ivan Cherednik, who will speak about Q zeta revisited.
Thank you. Thank you very much. So this is the plan, abstract actually, right? So this will be the main point. Questionable, I know. Why complex S have generally no direct arithmetic and geometric meaning here. But in process, what is superduality? There is no Nikita here. For instance, for Nekrasov's instantons, it is epsilon1 transposed with epsilon2. Something which many people know, mathematicians, especially physicists, actually. This I will explain, of course, carefully. And then in process, I will define, I promise, I will define elliptic whole polynomials, and then I will need this mysterious column here. I will explain later. Okay, so we're done with this, with the abstract. And let me go back. I need to explain a little something about the main point of this talk, of this lecture here. Definitely I need to do it because this is a little bit non-traditional, softly speaking. Okay, so what about zetas? What is the meaning of this question? Are zetas geometric and arithmetic here? What we know about zetas, so of course there are two main examples, classical Riemann's zeta, something which I am doing almost full time here, Hasse-Weil zeta, mod p, algebraic geometry mod p here. But the closest to my talk are Selberg's famous celebrated Selberg zeta, the count of closed geodesics, and the so-called spectral. Spectral one is very simple. Give me any operator, and I will put calculate its spectrum if I can. Sometimes it is difficult, of course, you know, right? And then I will form this spectral zeta. There are interesting connections, really very interesting connections. But on the other hand, let me focus on applications. Okay, good. Let's discuss spectral zeta. For instance, you want in any universe, let's consider Igor's universe, Igor's world. His works here, right? Let's consider, for instance, Riemann surfaces, Kp, and so on and so forth here. Zeta-functions of Riemann surfaces. But with whatever approach, still one of the key questions is to calculate the determinant of the Laplace operator. A version, a determinant of the determinant of any first-order operator, Dirac, for instance, operator, and so on here. Okay, still surprisingly, the best known way is to introduce zeta, exactly this particular zeta here, and then to do this formal combination, minus zeta prime x here, then extend it analytically to complex S's with some regularization, tend S to 0, and here you are, you will get determinant. Of course, in Igor's universe, so to say, right, there are possibilities to use quasi-periodic solutions, finite zone solutions, and so on and so forth. You can use it, right? But this is the most universal method which works practically always, especially with some latest theories and some exotic theories. So surprise, surprise, the simplest way is to introduce zeta, extend it, now spectral zeta, extend it analytically to complex S's, and then tend S to 0 here. Here we are. Then pretty much the same can be done, but this is non-trivial, with Selberg zeta. Selberg zeta is much easier to calculate, actually. This is complicated. Even for when lambdas are 1, 2, 3, n, there are quite a few operators with such properties. Still, you know, you have very complicated analytic number theory. Okay, but in one instance, let me just attach it, or something like this, right? It is really pure pleasure to calculate Selberg zeta here. Let's consider some special curve, which is h divided by gamma n. Gamma n is classical congruence subgroup. It can be SL2Z, but sometimes compactification is necessary. But let's just divide by gamma of n here. Okay, perfect, right? And then there is a famous celebrated Selberg's conjecture. Selberg, by the way, himself proved functional equation and Riemann hypothesis for compact Riemann surfaces. And he conjectured then if it is if this particular X Riemann surface is of arithmetic nature, then lambda 1, the smallest eigenvalue here, is greater or equal than 1 over 4. Himself, and then a bit later, people immediately realized the connection with so-called Grant Riemann hypothesis. If lambda 1 is smaller than 1 over 4, then immediately there is a counterexample to Riemann hypothesis. So close connections, but of course they look somewhat mysterious, right? Not only for those who see it for the first time, including myself, by the way, but even for specialists. We don't know, we don't understand how it works, but of course we have a lot of implications here. Okay, a little bit different example. Now Nikita is here. Ising model with external magnetic field. So this is, so to say, integrable universe, right? Now it is famous, or better to say infamous, infamously non-integrable. Ising model is integrable when d equals 2, of course, right? With d equals 3, we know. But when d equals 2, right, but still you add external magnetic field, many people tried, including my friends, and no way, it is non-integrable. We have solid evidence now based on effort and time. People spend solid effort that is non-integrable. Perfect, but still for any d, we have Lee-Yang theorem, the corresponding partition function in terms of complex fugacity. Fugacity is inverse time multiplied by Boltzmann constant, and inverse time and then multiplied by h, of course. External magnetic field here. Okay, so in terms of complex fugacity, it satisfies Riemann hypothesis, surprise, surprise. Now it will be unit circle, but this is equivalent for any d. Then conclusion. You consider log Zn, it is not physical, of course, n is the number of particles, so to say. Then you tend standard combination, log Zn divided by n goes to infinity here. This is physical now. And then you prove in some very strange way that it has no unwanted phase transition. So you have circle intersects with real line at one point, here we are. Very strange, very exotic way to prove that it has just one phase transition, no unnecessary condition. Then I played mathematically with this. I deformed this theory, I will not explain how. And then I found that for some parameters, when fugacity, e to fugacity becomes complex here, not complex, negative actually, negative, right? I found that still Riemann hypothesis holds until some moment, right? And at this moment, or a little bit to the left, you will have not just some unwanted phase transitions, you will have the whole segment of phase transitions. So the theory is definitely not. Nikita, you are laughing, right? This is physically, it is nonsense.
Before the moment and after the moment, only you can get to the left of the moment.
This is okay. This I can survive. Yeah, I suspect there's some physical whatever arguments, right? So far, makes sense. It makes sense, right?
Yeah, but what's strange to me is that the circle intersects the real line at one point.
Guys,
How,
whom?
To me, Vanya, to me.
Oh. I try. Go ahead.
How can the circle intersect the line at one point?
What? Unit circle, phase transition by definition can be only real, physics theory, you know, right? And then unit circle intersects with a real line here at point 1. Positive.
Okay.
Thank you. Positive, of course, positive, right? Okay, so interesting story, non-integrable, but let me very briefly, I don't understand quite a lot here, connect it with the beginning of the story, Selberg zeta here. So story is more or less like this. If you consider, just a second, Anton, doesn't work, but anyway, doesn't matter. The light, but anyway. If you consider Selberg zeta, right? Good. Yeah. So just to help you to understand what is doable, what is not, let's consider Selberg zeta for this particular example when it is divided by SL2Z. Then immediately you will prove that no need to calculate the lengths of geodesics. You need only to calculate the norms of hyperbolic elements in this particular group. Exactly, the length is something like lambda squared. Lambda squared is eigenvalues will be lambda to minus 1. Take the greatest one, lambda squared, right? So perfect. This combinatorial problem. So Selberg zeta in this particular setting connected with Ihara. I will skip the definition. Ihara's zeta function and connected with a lot of zeta functions associated with trees, with graphs, and with whatever here. And now it is connected with partition functions, right? At least morally. Okay, so there is a connection, but of course it is not clarified. Okay, anyway, my conclusion that whatever you are doing, right, you consider zetas, you consider them, you extend them analytically to complex numbers in this example, and then eventually you need to tend S to 0, or in arithmetic consider some other remarkable real values. So we don't, conclusion, right, questionable conclusion, so we really don't understand what is 1 divided by n to S. Right, because of S, of course we understand, but when S is a complex number, this is quite a problem. So the best way I know by now is to replace it by some invariants of length spaces here, which are very much geometric. You will see. Okay, so we're done with introduction. I already spent like 5 minutes. Okay, let's move. Right now it will be pretty much from scratch. What does mean from scratch? You don't like n to S, right? Try to generalize. So replace it. So what people did, the natural thing to do is just to replace it by Q binomial coefficient to S here, right? Q binomial coefficient simply replacing n by sine h of x, n, something like this. But this is not exactly what we are going to do. We are going to fix n to S when S is a complex number. But still, people do this, and at least they proved that the limit is correct. The limit when Q goes to 1. But we will do something different. We will use McDonald's measure here. So in a moment, you will see why McDonald's measure is a quite natural solution to the problem with complex powers. Look at the definition of complex power, what I already mentioned a couple of times. We're not happy, we're not happy. We're not happy with this particular formula. Look, just to divide U to S, you need a cut off, and then you need this combination, right? Moreover, if it is polynomial to S, it is quite long story. Berenstein set of polynomials, etc., here. This is simple, but still some unpleasant thing. Of course, classics of 19th century liked it, but not us. We don't like it because you immediately need at least some cutoff. You need to do something. Okay, so what is exactly the connection with N to S? Here we are. Stirling-Mock limiting formula here. Do exactly the following. Take this particular guy, then plug in, because of some renormalization reason, plug in square root of 8z here, q, and here we are. It will be minus z to k. So
what's cheap? You need to define a to the k, not to define c to the k. What's the point?
The point is that this is multi-valued and this is single-valued. In Q calculus, there are no multi-valued functions here. We use this combination as the closest. Gammas are perfect, you know, right? But complex powers are not. So this is single-valued function with some singularities, but this is okay. This is Q gammas. Q gammas doesn't matter, they are single weight. In Q calculus, there are no multi. And with this we don't like, and seriously, people didn't like it even in the 19th century, specialists in zetas and similar stuff here, because it is multi-valued, right? Multi-valued are fine with Riemann surfaces, right? Inevitable, but not here. Here you have lots and lots of problems. Okay, so here we are. Problem, right? Complex powers are multi-valued. Solution. Do exactly as I explained, use A, right? Then, of course, there is a classical stuff, which is absolutely necessary to mention. This is classical story when that Q gammas, this combination of Q gammas here, goes to gamma. Then why we need this combination? Because if you don't use combination, there will be log term. There will be some expansion, right? There will be something in the beginning, then dialog, right? Which we don't want here. And then, so you need to consider this particular very smart combination. The numerator is simply theta function, actually. But this is not theta function because it is plus q, plus k, and plus k2 times here. This is called truncated theta. Perfect, right? Then you do the following. You follow when Nishizawa here, you just consider delta minus s, etc., very simple to define. And then you'll have the second major feature of Q calculus. This function, just the definition here, will have dense everywhere set of poles, but otherwise it is perfect smooth function. if you approach any irrational or transcendental function, it will be nicely defined. In my programs, I use the test of three points here. I consider 3 points, right? And take 2 when the values are as close as almost coincide, right? So what is the trick? The trick is that when you approach transcendental function, the corresponding residues go to 0. Poles are here, but residues go to 0. Another, I decided I discovered some exotic examples, but then later I found that these exotic examples are pretty much common here. It is, we have lattice with 3 generators. So in this particular definition. But of course I don't like it, and then of course I will immediately switch to integrals. With integrals, of course, there will be no some such exotic features. Okay, here we are, Q zeta, but first let me discuss what I'm going to deform. This is basically zeta, but not exactly as you see, right? It is plus zeta, actually the simplest L function, right? This is actually eta function, but I will discuss eta function a bit later here. Okay, so this is from the second proof of functional equation, Riemann's proof, right? So here it is, right? Consider the following integral, classical stuff here, and they will get exactly zeta, corrected by gamma, and corrected by this vector, which is the price of plus here. If there is no minus, if it is minus instead of plus, it will be just zeta multiplied by gamma. Okay, and my formula is here. Now you understand perfectly that I placed x to k by delta k, right? I integrate. Now in the imaginary direction, there are 2 theories, not 1. Here does matter, but here we have real, the so-called non-compact theory, and compact. This is compact. This is integration in imaginary direction. Here we have the definition. Immediately the theorem, right? The limit is just fine. Consider q. Q goes to 1, a goes to infinity. So here, why is this so strange? But it works. So far it works. Okay. Later I will ask Vanya, but no, not now. Okay, when a goes to infinity, meaning q goes to 1 here, right? So the limit is fine. Everything is just for absolutely arbitrary. Anyway, I need to describe. Non-arbitrary, I will explain. Okay, so immediately there is a warning. What happens if you take here minus? Then we have something interesting. So, okay, let me try what Vanya explained to you. Maybe here, right? It's strange. Okay, let me just do it here. Okay, if you do it with minus, aiming at zeta here, then it will, apart from critical strip is s equals k plus 1/2. It is clear here, right? Then apart from critical strip, it will go to zeta. But inside it will go to some function which is essentially gamma. There is a phenomenon which is called as a phenomenon, maybe I can skip it. Okay, let me skip it. There are some interesting implications in analytic number theory of this very observation here. Okay, perfect. So let me skip it. Let me go to the next page. Okay, warning, simply warning, right? Be careful, because with plus convergence is granted, but if it is not, then you need to do something. Okay, so here we are, the first point. Then phenomenon, which is the end of the problem here. The problem is that there is a strong tendency, almost Riemann hypothesis, the strong tendency for the zeros to go to the left. Very strong tendency. If all zeros of q zeta go to the left, then it is the end of the story. It is the proof of Riemann hypothesis, of course, right? But this is just a tendency. Moreover, if you do it systematically, you will calculate the first derivative. The formula is here, and then you will see that for the first time, this thing is negative. Anyway, for the first time, the linear approximation go to the right is 1977/27. Which is a famous zero of zeta function, exactly when there are two very, very close neighboring zeros here. There is a standard fact from 19th century that if the zeros are very close, a critical line here, very close to each other, then it is counterexample to Riemann hypothesis. So here we have the first suspicious pair of points. So this is pretty much perfect. Makes sense to specialist analytic number theory. Okay, so here we are. Right? Unfortunately, it is absolutely impossible to calculate practically q zeta in this business, but I will discuss the examples when you calculate it much better, much faster. Okay, so here we are. But first version of Riemann hypothesis. First derivative is no good at 1977 here. But on the other hand, there is no theorem that the whole Taylor series converges, so probably the second derivative will correct it somehow. Anyway, we don't know, but the evidence is that the track is right. then let me do the following. I will not discuss Rogers-Ramanujan identities definitely today, but there is interesting Rogers-Ramanujan identity occur when anyway, when real part of k goes to plus infinity. Then upon some modification, this thing is actually Q modular function. But this I am going to skip. Okay, so let me skip completely this theorem, right? But on the other hand, still, you see derivative can be calculated. Very interesting derivative. All values of zeta in this derivative, in this particular derivative, all of them are apart from critical strip here, which makes perfect sense. Okay, let me go to the next. I'm saving time for this column. Sorry, guys. Just skipping something which is not absolutely necessary. Okay, perfect. Analytic continuation. Now the business about analytic continuation. This is interesting. So then it makes sense to switch from delta function to so-called truncated theta function, which is mu. Mu stays for measure, for McDonald's, for whatever, and it will be measure, right? Pretty much the same story, but on the other hand, still you will notice, like in theta function, you will notice +1 here, right? So this is exactly the difference. So now numerator is really a theta function. And here we have not theta function, but again, let me repeat it. If it is k here and would be minus k here, then it is theta divided by shifted theta. But this is different. This is just combination of q gamma function here. Okay, so then basic examples. Now I'm going to integrate with this measure. Capital F here, so it can be Gaussian, it can be Gaussian multiplied by reasonably good Laurent series here, or it can be something which I need for zetas, E minus and E plus. E plus will be our main guy. Okay, so the theorem, now it is about analytic continuation. So if it is about this particular integral, right, it is analytic, and of course convergence is granted to zeta here, only in this range. Real part of k must be greater than some small negative number. Positive real k's are perfectly okay. Okay, so why? I already mentioned that there are no multiple varied functions, all functions single varied. Why I need to do anything? Why we have some problems with this particular one? Very simple. We have vertical integration path here, and then we need to avoid exactly this bad case, or exactly this particular C is the integration contour here, shifted in some negative direction. Exact calculation. So anyway, you cannot go through the wall. Walls are exactly here, right? So you have walls, but fortunately all of them are belong to negative part here. If you play with epsilon, you will see optimal. You will find optimal epsilon here, which is 1/4. We are doing A1 right now. No arbitrary roots. So, so perfect. So two comments here. All right, this is just about the limit to gamma function here. So we have analytic continuation, the technique of analytic continuation, and then we have straight analytic function, straight analytic integral. When real part is greater or equal than -1/2, then S is k plus 1/2. So we covered critical strip. Then I will show you how it works for arbitrary systems. You will be really surprised, I believe. I was surprised. I found it recently. Okay, let me go to the next page. So what is the meaning of this page? So now we understand that integral nicely behave. This I decided to skip before here. Nicely behave when the real part of k is greater or equal than -1/2. And then there is a technique of analytic continuation, which is essentially picking up the residues. In Q calculus, any integrals can be calculated as sum of the residues. So it is pretty much what I'm doing in my papers, including the last paper. Okay, now let me show you something which is much nicer for practical calculations. So let me replace the imaginary integration by the corresponding real integration. This is exactly this particular shape, which is shown graphically here. Classical stuff here, right? And then it is well known that you will get analytic function or meromorphic function anywhere, right? This is exactly what I'm doing. Let me try to adjust this. Oh, here it is, right? You see some kind of sign of this particular contour, right? From infinity minus epsilon I, epsilon is a small number here, to infinity plus epsilon I, right? Classical contour of integration. So you integrate, and then you will immediately calculate. You just Cauchy theorem, nothing else. You will get this nice formula here, which is extremely good, even when A is like 750. You remember, Q is e to -1 divided by a. So it is very close to 1 here. Still, calculations are very fast, very reliable, unless it is about big imaginary parts of k here. So this is exactly the formula, which is a sharp zeta function. A bit later it will be a Jackson integral, Jackson summation, but later, not now. Perfect. So here we are, pretty much a counterpart of the previous theorem, but now it is real theory, real integration, right? Here we have the limit. The limit can be calculated. So far, so good. And of course, the formula is real nice now. Much you don't need to calculate. And then, of course, it is real integration. Real integration is just the other way around. Zeros definitely prefer the right-hand side. Look at this particular picture, right? This is sharp, this is zeta. This is sharp. This is the first example, classical 14.13. Classical first zero of zeta function. A is big enough, 750. So then here we have classical stuff. Here, first, of course, we have this one. Then we have 21, 25, etc. This is exact zero of sharp zeta, and this is linear approximation. Good, but of course there are no theorem, and I don't expect any theorem that the whole Taylor theory converges. Here, somehow about 88, of course there are some discrepancies, but still linear approximation is good enough. Okay, but anyway, the point is clear. Zeros definitely prefer now the right half plane. Half plane here is very easy to control. K is better than S. K is 0. Critical line is real part of K is 0. Okay. Then we are approaching actually almost the end of this part of the story. Then I'll skip to revisited part. So Riemann Q hypothesis. So we are already reasonably happy, at least I was reasonably happy, with the statement that zeros go to the right, zero goes to the left. Sarnak in one of his papers mentioned that actually we don't need Riemann hypothesis. We need only the fact that there are no zeros in the right half plane. In one of his papers, he mentioned many things actually. But Peter wrote fantastic papers about this stuff, including for Selberg zeta. Read his notes actually, right? It cannot be better. And anyway, Peter Sarnak mentioned this is exactly what happens. So we have some theory when zeros definitely prefer the right-hand side, which is the end of the story, of course, right? But unfortunately, we don't know how to prove it, but this is what any reasonable person can expect. Okay, now I'm showing you Dirichlet function, the passage to the Dirichlet function. Definition is very, very simple. This is Dirichlet function of conductor 3. Right, classical stuff, recalculated to K, not to S, but recalculated to K. So here we have pretty much the same sharp Dirichlet function, some remarks about the convergence rate, and then good news is that the first bad point when derivative is not to what we want here is only 246, not 17 something, 1700. So this is basically can be calculated, but I didn't retry it. So it appeared to be difficult, but still doable with good computers. Still it is doable to understand what do we have. Is it really like some kind of conjecture? Do we have a conjecture? If at 246 zero goes to the left, the end of the story, we need to use something else, right? So perfect. This is how to go to L functions, which is of course valuable itself here, and then of course what can be expected, right? Let me show you what can be expected. Now let's try to attack the true Riemann hypothesis, which is about that all zeros belong to the critical line. Critical line here again is K equals 0. Real part of K equals 0. Okay, let me show you calculations. So far so good, right? But of course, the range is not what Adlishko can reach or whatever. He can reach easily millions here. For this particular business, I reached only some modest values. But still, you see, pretty much everything is okay. But anyway, basically, let me just show you this picture. Right? Let's enjoy it for 2 seconds, right? And then let's go to the next page. This is the reference of the original paper. Good. So now we go to revisit part, and now I have time, almost certainly I have time for many, many things, including elliptic-Hall polynomials. Okay, so the first point here is Q meta-Macdonald or Cherednik meta-Macdonald formula, which is difference counterpart of famous meta-Gauss integral formula. Okay, I need to introduce the same mu actually, right? But now it will be for arbitrary root system. You can see here, oh no, it's not, maybe it was not because of me. Here it is, right? This is now standard stuff, arbitrary root system, but reduced root system, reducible use here. Here is the general definition. Pretty much the same material you see, right? Shifts by J, but this is general version when we assume that there are two lengths. Concerning lengths, and now it is McDonald-Daha theory, right? And I need to say something about parameters. Maybe now it's about time to say something about double-fine Geek algebra, right? So what is this particular guy? This particular mu function makes basic operators of double-affine Geek algebra unitary, right? This is the claim, but now let's discuss parameters. This is interesting. So first of all, we have Q because it's different theory. Then we have T because of these translations. Here you have, right, some kind of guys here, T parameters here, some new parameters. Am I right? Maybe I skip something. So first, of course, it must be multiplied by T is here. Perfect. T is here, right? So we have Q parameter and we have T parameter, right? What else? If it is not ADE, then we have two T's, one Q. But we can move up to one Q and four T's, which perfectly matches famous beta-type Selberg integrals, which contains 5 parameters here. So we managed, so to say, right? We have some kind of sample, classical sample. Selberg was a absolutely fantastic mathematician, of course, right? He provided us with this 5-parameter deformation of beta integrals. Here we can do it. Basically, we can do it now. Okay, so this is exactly about K long, K short. We have two roots, two types of roots here, two lengths, short and long here, and this is a general formula for long and root. T alpha means it depends only on the length of the root here. So here we are, mu function, which makes operate. What is Daha? Can I give a definition? Yes, I can. Daha is a universal deformation, two-parametric deformation of Heisenberg, or one-parametric deformation of Weil algebra. Weil algebra, to be absolutely exact, extended by Weil group here. So the mathematical theorem, and not a difficult one due to Aleph company here, that they can be locally, they can be only deformation with two parameters. There is nothing else, right? Then a bit later we understood that Daha provides universal formalism for practically any Fourier transforms, not only those in terms of spherical functions, all of them, right? Verlinde transform was a confusion. Of course, there are some Fourier-Mukai transforms from algebraic geometry which are different, but all other Bessel functions, hypergeometric ones, all of them, right, were supposed to be covered, right? And this is exactly the confirmation. This table is classification. Anyway, what is Daha? Universal deformation, two-parametric only two parameters are possible unless we do some exotic root systems here. Universal deformation. So pretty, they say, I mean, my predecessors say, Fock representation, I use the same words, but for me it will be called polynomial representation or polynomials. Then if we go to elliptic level, I will say something about elliptic homology, then it will be so-called Layenha polynomials, which are serious here. That's it, right? They will be polynomial representation in Layenha functions. Okay, otherwise everything is absolutely okay, pretty much the same. So anyway, with VEC here in Daha theory is called co-invariant, right? Again, just different terminology. Perfect, right? And then now, let me explain this point. I have time for this. Let me explain that Nikita somewhat simplified his life. Actually, he knows, of course, perfectly that there are 9 theories, 9 quantum many-body theories. Now I go to something when I cannot use this guy here. Look at this particular column, right? This is diamond, right? The claim is that we have absolutely all integrable quantity many-body, nothing else, because Daha is a universal deformation. First. Then we know from soliton theory, including Igor, we know that the most complicated representation of the zero curvature are elliptic. There is nothing else, right? Then there are many instances where elliptic curves are. So, by the way, Daha is directly connected to the elliptic curves. It is based on fundamental group here of elliptic curve with one puncture. This is basically it is Daha. Then in post-quadratic relations, you will get Daha. So anyway, elliptic everywhere, right? And there is no escape. But there is something interesting I will show to you. So what is exactly how to read this particular diamond? Very simple. ER functions are elliptic, operators are differential, differential, right? What is Macdonald theory? 3 of them have special names here. Macdonald TT. Functions are trigonometric, Laurent polynomials. Operators are trigonometric, meaning difference operators, right? Then RE. Functions are rational. And then operators are elliptic. P function from Nikita's lecture here of ddx here, whatever it is. Okay, so what do we have by now? So check means known. ER and ET were defined in my papers here. Only Daha was used. No toroidal algebra, no elliptic algebras, no nothing, literally, you know, right? Then TT is, of course, well-known track here, McDonald, right? Best of RR, operators are rational, functions are rational, Bessel functions, to be more exact, multi-valued Bessel function here. And then let's approach to the bottom. What is the bottom? ET. Let me spell it. Functions are elliptic, operators are difference, relativistic in Nikita's lecture here. TE, same, but functions are trigonometric, operators are whatever, right? Dot and dot means that definitely we know these guys here, because general stuff here is that there is Fourier transform. ER and R connect with Fourier transform. Fourier transform is a tricky thing. There are books and books even about classical Fourier transform. There is something to do here. But still, first principle, this Fourier transform connects the corners here. So this theory and this theory connect by Fourier transform. Of course, it is well-known Harish-Chandra theory about the first line here. TR and RT are connected by Fourier, which is Harish-Chandra Fourier transform, actually, right, with some extra parameters. Okay, now let's approach this particular block. Here dot means that nobody did it, actually, right? But this was done, at least theoretically. With ER, it is much better. I calculated a lot. So here we are, right? So the ultimate theory, elliptic theory, right? Operators, functions are elliptic, operators are elliptic, right? Problems with convergence, anyway, most formally you can put write something, but it will not work. It will diverge everywhere, you know, right? What is the name of this guy? Physical name. X theory D equals 6. Here, presumably it is D equals 5, Bogomolny equation, what Witten did here. Presumably, with D6 it is, I need to explain. But X theory is pretty much obvious that we need to call this guy X theory. X theory from physics, X theory.
What is X?
X, it is called X, unknown, whatever, mysterious. Awful, right? D equals 6. Okay, we'll discuss it later here. But anyway, in physics, it is really elliptic.
It gives a solution to the equations that we can write. So we have a solution.
Good. This makes perfect sense. So good that I deleted this. It is from our joint proposal to whatever. Not my name, actually. Mina, some people. Anyway, it doesn't matter. Forget it. D equals 6. And this is the level of D equals 5, presumably. Bogomolny equation, what Witten likes, actually, right? But anyway, something like this. But this is question. This is ultimate theory, right? And here you agree, elliptic is supposed to be the last. With one reservation. So if Q is a root of unity, you automatically in this table, you go to the next level. Rules of unity provides, for instance, if you want to go from trigonometric to elliptic, consider trigonometric at roots of unity. You will get, essentially, you will get elliptic theory. So maybe there is one more possibility. Elliptic at roots of, and Q is the root of unity here. But there is nothing else, right? Because of multiple reasons, we expect that that because of this fundamental principle, there is only one deformation of Heisenberg, which is Daha, universal deformation is Daha, and because of other instances here. Right? Integrability stops here, but on something begins. This story begins here. Non-integrable theories. Okay, so this, and then let me say something about cosmological connections. Many connections here, definitely. Flavors, I don't discuss flavors, is one of the flavors here. Q can go to 1, T can go to 0, infinity, many of them. Many flavors here, but this is interesting, right? Let's look at the middle, for instance, block here. So here, if you read it cosmologically, it will be elliptic cosmologies of G over B, classical flag variety, is connected, actually isomorphic, but you need to do something here, of course. A K theory, which is trigonometric cosmology, right? K theory of G over B hat, trick, right? If you continue, you will get regular cosmologies of elliptic configuration space, right? Of elliptic configuration G over B here, right? But I will not continue here. Okay, and then you can spell pretty everywhere, anything here. And this is, of course, something monstrous, right? Elliptic homologies of elliptic configuration space here, right? But on the other hand, it is quite available, I believe, not only to some people in this room, right? Doable, right? But it can take time, of course, right? To understand what is it. With elliptic homology, the approaches maybe not too mysterious. You replace Andrei's talk. He considered for homology polynomials, invariant, double invariant polynomials, K theory Laurent polynomials, are invariant polynomials, and elliptic level is Layenko polynomials or invariant Layenko polynomials. And there are some axioms due to Kapranov, some other people, you know, right? Axioms which pretty much, for simple example, pretty much sufficient to extend this here, at least to know the expected answer. Okay, so this is definitely this expected answer, right? And moreover, there are some papers for in particular examples when it is checked. Okay, perfect. So this is what I was going to say. And then what are elliptic-Hall polynomials? The last. Anyway. So here we are, right? It works now. Just standard definitions. Here we have what I consider the key Daha formula. This is exactly Q McDonald meta, right? Let's read it together. You integrate Gaussian, right? Gaussian with minus to ensure the convergence here. Any function f, reasonable function, then you multiply it by Macdonald's polynomial with symmetric setting, normalized as such. They are called spherical Macdonald polynomials here, and the claim is that you will get f x at lambda plus rho. So shift by lambda can be provided by integration with p lambda here. If you think a little bit, this is pretty much meta formula, but meta formula with some kind of identity, but you with Bessel's. So what is the main formula from classical analysis? Bessel by Bessel time Gaussian, integrate with measure x to 2k here, you will get the first p of this of mu, p of mu. Bessel lambda, Bessel mu, integrate with the Gaussian. The measure is, of course, must be classical Bessel, x to 2k here. The answer will be p j of lambda evaluated at mu. This is absolutely the main formula in Fourier analysis of Bessel functions. This is pretty much the same formula. Okay, so what are elliptic Hall polynomials? So first of all, I need to induce Jackson integration, which is simple. You need some invariant function. Of course, invariant function can be only like this. Summation over all affine Weil group. Over the lattice, if the function is invariant, and over the lattice. Jackson integral, just summation. Instead of gradation, you have summation. So what is elliptic Hall polynomial? In what we discussed before, including this particular formula, replace integration, image integration, by Jackson summation. You will get exactly definition of elliptic Hall. Sasha is not present, Braverman, but there was a nice paper here, Braverman, Kashdan, and Manish Patyak, if I remember correctly here. They try to introduce double p-adic group here. Anyway, interesting story here. But anyway, but first of all, of course, let me mention Kapranov, at least Kapranov in this business. So this is definition, guys. Daha's attack isomorphism. The number of elliptic Hall polynomials coincides with the number Kac-Moody characters of level L. Exactly. Because of some periodicity. But anyway, not many, lambda potentially, there are infinitely many of them, but you don't need so many, right? You need exactly the number which is equals to the level L here. Okay, so elliptic Hall polynomials. Let me, what is the place of elliptic Hall polynomials in this picture? This I can explain to you. You go to this level. At this level, you will get elliptic Macdonald polynomials. A little bit unpleasant, I must say, right? And then this is when you kill one of the parameters. Then you will get elliptic Hall polynomials. So somehow transitional here and here. Okay, perfect. Oh, by the way, concerning this particular one, about 5-6 years ago, I found a paper because I was a referee. The paper found me, to be more exact, when they suggested absolutely reasonable approach to this particular problem. Basically, not only for specialists or not only for specialists, for those who are interested and want to continue, basically, instead of series, they consider values, functions as values at some special points. This worked in their paper. I immediately understood the potential, but didn't do anything actually, right? But still, there exists a paper, right? Practically unknown, but I know I know this, right? When there is some very good remedy, how to manage this particular guy. Forget about series, consider values. Values are some special points here. Then you can manage it, right? Then there will be no convergence problem. For instance, they defined in the same way Macdonald polynomials, right? As functions at some special sets of points. Somehow connected with Andrei did long ago here with Grisha Alshansky about interpolation polynomials. Interpolation polynomials, by definition, means functions as some sets of points here. But anyway, good story here, and then presumably we have something else at roots of unity, but this is different. Okay, here we are, the definition of elliptic Hall polynomials. You see, elliptic Hall polynomials is literally what we are going to consider during the remaining 15 minutes here, but if just for different choice of integration. And by the way, this Ajax integration is pretty much closely connected with what we did with sharp zeta functions when the contour was like this. Summation, anyway. So very good. Now we are approaching actually the end, right? Here we are, right? Now for arbitrary root systems, for any given reducible root system here, we come with this definition of Z plus. Z plus because we are deforming eta function. Well, again. Okay, good. No, again it switched to does work. But anyway, I cannot use the cursor here. But and I'm not tall enough to reach the top. I'm good, but not that good. Okay, so the first line, guys, definition, right? The denominator can be exactly calculated, some nice product formula, which is exactly McDonald's method, exactly. Good. Thank you. Okay, then let me introduce this letter S, right? And I'm going to calculate the limit. Right? How to calculate the limit? This is pure elementary and very simple calculation. I need just to calculate the number of positive roots, long and short. So statement, right? Just very simple. It is in the limit. It will be, for instance, you can ask, can we generalize zeta function to arbitrary system? Yes, you can using the same e to x squared, etc. here. This integral can be immediately calculated, reduced to one-dimensional integral. But you need to count the number of positive roots only, right? Because mu function contains products over positive roots. So this is short roots. This is about long roots, and n over 2 is just because dx. Dx now is vector, of course, right? So this is the formula, and the answer is like this, right? The limit nicely exists, and it is exactly eta function. Eta function, by definition, it is plus zeta function. 1 minus 2 to minus s, zeta of s here. S is so what is s? It used to be s k plus 1/2, but now it is like this, right? Then surprise. Now we play with epsilon, right? Epsilon because of the same reasons to improve the convergence of the integral. Later we'll do meromorphic continuations, but later. But can we just save this integral as much as possible? So now let's assume for the sake of simplicity k long equals k short, or simply AD. Fine. Then the claim is consider this particular guy rho divided by h, Coxeter number here. This is the best, the optimal. And then this integral will converge an analytic with nice properties here when real part of k is greater than minus 1 over h, right? Then surprise for me at least, right? You plug in, you will get the corresponding value of s. Look at an. Here I calculate for an here, right? For an, right? So this is exactly v or whatever. Let me call it v is Coxeter number here exactly. So v times v minus 1, literally the count of positive roots here. And then let's plug in minus 1 over v. Let's add the guy which is responsible for dx here, and you will get 0. Perfect. So this integral, as we already observed, is well defined, analytic, convergent, everything, right? Within the whole critical strip here. So if you wish, it is the second, the third, the fifth alternate definition of the Coxeter number. So this is exactly how Coxeter number appear, right? Coxeter number is the value of k. Look at this particular guy here, the value of k, such that s is 0 here. Definition, right? But for me, it was a little surprise here. So you see, I decided to show you this calculation, trivial calculation in full detail. So you calculate here, right? And then again, eventually you will get 0. So perfect, right? We cover the whole string here. And then immediately there is some suggestion to use it for Kuehl-Lindelöf conjecture. What is the Lindelöf conjecture? Very approximately. That the behavior of zeta function in the critical strip is pretty much the same as apart from critical strip, right? Grows, but very slowly, actually, right? Like t to whatever, I will skip the definition. So here we have the integral which does not distinguish between critical strip and something to the right, right? Perfect. So if you have any estimates of this particular stuff, then you have some qualitative suggestion, but I have something better than this a bit later here. Then you have some qualitative at least suggestion, right? How to approach Lindelöf, because we have the theory which doesn't distinguish when critical strip is nothing. There is no critical strip, actually, right? Integral representation works. Okay, then the little calculation, but I need to do something explicit here about an, right? For an, v is n plus 1 Coxeter number here. Let's introduce this guy just technically. V circ equals minus kv here, right? then you calculate S. Nice recalculation, right? Then I use this calculation, of course, below here. And then we have some interesting, strange duality. V goes to V naught. Look at this particular guy. So S, we have duality when V goes to V naught, and K, anyway, I will state it later. But right now we see that there is some duality between V, which is Coxeter number, and with something which is absolutely not Coxeter number. It is minus KV, negative whatever. But we have Deligne theory, we have Daha theory, we have super polynomials, and it is GLT. According in Deligne's terminology, it is a story about GLT, when T can be arbitrary complex. Not GLN, but GLT here. But let me show you this exactly what I already mentioned to you. So what exactly epsilon 1 to epsilon u duality here. Let me show it to you. Almost a theorem. So there is stabilization. This formula which we found actually depends only on Coxeter number, literally, right? The claim is that there is some triple function qt of course and a such that if you plug in t, if t is q to k, but this is standard for us, and if a is t to v, Coxeter number here, that these things becomes exactly the polynomial we considered before. Exactly. Anyway, it depends uniformly. It depends only on the Coxeter number. So we say that this triply graded generalization, QTA formula. Okay, and then theorem, but this is solid part. This is the existence of ZC requires little analysis here. The theorem is that we have superduality. Superduality here is T goes to Q minus 1. Here it is. Q goes to T minus 1, Q minus going to T. So it is very well known that it's pretty much the same as epsilon 1 goes to epsilon 2 for in terms of Hilbert schemes of C2 and so on and so forth, right? So this is superduality. Of course, superduality is absolutely the key conclusion from Havanus theory, from the theory of superpolynomials, practically anywhere. Then you do the following: you substitute, right? And then you will see that this superduality, exactly V goes to V naught, exactly. Minus KV here. In the limit, it appeared that K goes to 1 over K, of course, because Q goes to T, T goes to K here, right? Then V goes to this particular. This is exactly the symmetry of the formula for zeta function. What could happen if there is no such symmetry here? Then we have a contradiction in mathematics, because we have some kind of connection between different values zeta function, which is impossible, of course, right? We know that these particular two different points must coincide in the limit. This is exactly what happens. So this is expected, but still nice straightforward calculation. And then almost the end of my talk here is now we have something interesting. Now we have new possibility. Instead of considering GL2, what is GL2? SL2. A equals T squared. What is SL3? A equals T cubed, and so on and so forth here, right? But it is much more reasonable. We know this from the theory of super polynomials, not invariants, link invariants, and so on here. We know very well it is much more reasonable to consider when A is 0, to consider some different track here. Here we are, right? So you have new possibilities, new potential, and still K goes to 1 over K, which is potential connection of big case and small case. This is another vision and much more realistic, I believe, approach to state maybe not exactly to prove the classical Lindelöf hypothesis, but to state at least Lindelöf hypothesis in this particular setting. Okay, another possibility, another new interesting story here, and then the end of the story that what we discussed analytically is actually directly connected with invariance of length spaces here. So what is a length space? Very easy to define. You have C2 with two coordinates with x and y, and x is subject to action of roots of unity, right? Then you can restrict it to the unit sphere here. You will get length space N1, which is non-trivial, of course. Okay, so this is what I suggest is connected with what Sergei Gukov called, or maybe not only him, Z hat, etc., etc. here. So this is the simplest example. When we have something which is expected, actually it is invariant, triply graded invariant of length spaces here. So here we are. We begin with 1 over n to s. Eventually it appeared, after this long, very much analytic theory, appeared to be ln1, so entirely algebraic something. But in what sense? So anyway, before finishing my talk, still I have 5 minutes, right? Let me just realize the next page actually, but I prefer to make it like this. So some long story. Eventually, it appeared that it is invariant, right? Some invariant super polynomial, right, of length space here. So now it is entirely geometric, right? Exactly 1 divided by n. So we eliminated S first, right? Replaced it by some Q, added Q here, then T appeared, then A appeared. So this is pretty much the end of the story. Do we have a theory? We don't know much about triple grade invariance of length spaces. This is next level here. Of course, we know what to expect. They expected some nice modular, not exactly modular, more complicated than modular function. But then they are serious. They are not polynomials. There is no question about it. Okay, so then geometric challenge is to find some kind of M, who knows, conifold, right, such that there are special fibers like fixed points or whatever here, if we are aiming at localization in proper cohomology, such that we can just consider cohomology of this particular guy, can be complicated, who knows, right, such that eventually you will get exactly this particular interpretation. So again, there is absolutely no problem with one particular guy, but the classical problem is that we consider summation of them, right? Do they appear in some manifolds? Of course, it is about length spaces are 3-dimensional. They can be embedded actually in 4-dimensional, but 5-dimensional is granted, of course. They can be embedded naturally, but are there some remarkable fibers, and can we use some kind of localization? Which cohomology? All these questions are, of course, open. Essentially, I'm done. Do I have anything to add? No. Let me go to the last page then, right? The first is more or less what I summarized. Sorry. Don't focus on the second. We'll discuss this juicy picture a bit later here. But first, something mathematical. What we really achieved. We did not somehow, instead of generalizing L functions, we created some kind of construction which combine modular Q functions, which are limits at t when t goes to infinity, with L functions, right? So we have something when the first arrow, which is the limit q to 1, which we discussed, actually seriously discussed, goes to L functions, directly L functions, and the second limit, which I discussed only vaguely, when t goes to infinity, then it will be modular functions. So here we combine two theories in one. Of course, everyone understands that there can be some Milin transform, but this is well beyond what we see in this picture. Okay, so this is exactly some kind of unification, not exactly deformation of zeta function, not exactly deformation of modular function, but unification. And we sacrifice modular equation, we sacrifice s to 1 minus s here. Instead, we have something else, something very interesting. And then this is a smart way just to show you what we are doing here. So smart way to present Riemann hypothesis, any kind of Riemann hypothesis, but in our business is Q. So what do we have here? So here we have real direction. So here we have imaginary direction, and then I borrowed it from some classical papers here. How to present, how to visualize that there are no zeros of something in this business. It is this is exactly our zeta q. In the right half, this is imaginary zeta q here. In the right half plane here. So suggestion, well known to specialists, I believe, is to consider the following: consider the real part multiplied by the imaginary part, right? Then, if there is some zero, you will immediately see the cross, very absolutely obvious cross here, right? There are no crosses, and the picture is reasonably smooth. And then, according to what I see, I'm done. Yeah, am I right? I still have 5 minutes. Okay, I'm done.
Yeah, thank you. Well, let's thank the speaker. Questions, please. Questions. I have a question. I have not caught explicitly whether each zeta function can be extended to the right of the strip or half plane it is defined at.
Yes, in this business always, the meromorphic continuation is more or less goes through total pole decomposition. In Q calculus, always you can use Cauchy theorem, right? This is more or less what I'm doing, right? And then it's not a problem at all. It is, technically, the answer is that there is classical Hasse-Weil, Arthur, Heckman, Obdam, how to say, picking up the residues technique. This is what I'm employing here, right? Analytic conditions are meromorphic conditions. But I claim that we have nice behavior of the integral themselves. which is can be some optimism, at least for specialists, right? Concerning Lindelöf or whatever.
Okay, more questions? Please. Yeah.
Sorry. So by that graph. Yeah, so. Conditionally, Nikita can say more here, but still, potentially, Nikita will discuss a parallelism between gauge theory and between quantum many-body theory in his lectures here, right? So the last destination is elliptic quantum many-body, which is, so to say, elementary. It can be discussed. Divergent, but still, he exists, right? And then it is up to Nikita to explain which kind of physics D equals 6 whatever theory, right? Which is exactly, and this is presumably this is the last integrable theory, period, right? Whatever we are doing, we cannot go beyond this with one reservation. At truth of unity, there is one more step here, and who knows what happens to truth of unity? You have four epsilon 1, epsilon 2. You mean?
If you remember, we discussed with you in Stony Brook.
But in non-integrable, right? We failed. We tried to. You mean integrability? There are some other things.
No, there are things which are not related to elliptic curves. You can, there are simple things which you can define over the rational curve, and then you have many parameters.
Not very many, but still, I know about 4 epsilon, some other parameters. They will not live
to the double elliptic system. Definitely not.
Yes, there are some remarkable identities, absolutely true, right? But concerning the what is the integrability naively? Fourier transform, nice theory of Fourier transform. This is integrability, right? But anyway, this now it will be his part of the story. He will answer all your questions.
Okay.
Thank you. Yes, please.
What does it mean P in theory?
TT, trigonometric.
QMBP. What is P?
Quantum many-body problem.
Problem.
sorry, guys. QMBP. Right?
Okay, I'm afraid we have to stop here, and how we will attend the next
Sasha, you
talk.
Riemann, right?